Section 3.6 is solving systems using matrices. I can represent a system of linear equations with a matrix, and I can solve a system of linear equations using matrices. Big ideas here. Matrices can be used to represent and solve a system of equations without writing the variables. The matrix row operations of adding rows and multiplying by a constant are equivalent to the addition and multiplication properties of equality. A matrix is a rectangular array of numbers. We usually display the array within brackets. The dimensions of a matrix are the number of rows and the number of columns in the array, as shown on page 174. So, if we have a matrix here, matrix A, we have a row 2, 4, 1 and a row 6, 5, 3. We have a column here, 2, 6, a column 4, 5, and a column 1, 3. So here we're going to say this is a 2 by 3 matrix because it's rows by columns. So 2 rows, 3 columns is a 2 by 3. Each number in a matrix is a matrix element. We can identify a matrix element by its row and column numbers. So in matrix A here, A12 is our element in row 1, column 2. So it's where these overlap. Row 1, column 2, that gives us a 4. This element is a 4. Okay, the first numbers are row, then column. Row, then column, and we get a 4 there. In example 1, we're going to identify our matrix element. We want element 2, 3. That means row 2, column 3. And where they overlap here is at 8. So 8 is the element we're looking for. Using the same matrix now, find element 1, 3. Feel free to pause there and give it a try if you'd like. Remember, the first number is our row. The second number is our column. So column 1, column 2, column 3. And 17 is what we're looking for there, where they overlap. So 17 is element 1, 3. We can represent a system of equations efficiently with a matrix. Each matrix row represents an equation, and this is shown on page 175. So here we took this row and rewrote it with just the coefficients. Okay, so the last column represents the constants to the right of the equal sign. So we replace the equal sign here with a vertical bar, and our constants go from the first equation into the first row, from the second equation into the second row. The other columns represent the coefficients of one of our variables, and we go alphabetical here. So since I have x's first, I'm going to take my coefficients 1 and 3, and they go in my first column, 1 and 3. The coefficients of my second variable are 3 and 1, so 3 and 1. And we again draw a vertical bar to replace the equal sign, and we put brackets around them to show that it's a matrix. Okay, so put a bracket around them to show it's a matrix, vertical bar for our equal sign, our constant from our first equation, constant from our second equation, and then the coefficients of our variables in alphabetical order. So here we're going to write this system of equations with a matrix. So instead of having our bracket here to show that these go together, with a matrix we put them inside brackets. So instead of the curly bracket to show our equations, we're going to switch to brackets. My equal sign I'm going to replace with a vertical bar. Next, I'm going to make sure both my equations are in standard form. I'm going to take the coefficients, 2 of x, 1 of y, and my constant for my first equation. For my second equation, I have 1x, negative 6 with the y, take your sign with your number, and negative 1. And that is our matrix. Same idea here, except we have 3 different variables. I have x's, I have y's, and I have z's. So I'm going to end up with 3 different columns to the left of my equals. In my first equation, I have 1x, negative 3y's, 1z equals 6. My second equation, I have 1x, 3z's equal 12. So I put a 0 in for my y there. My third equation is not in standard form, so I'm going to add 5x to get it in standard form first. and I have 5x plus y equals 1. Now that it's in standard form, I can switch it over to the matrix. The 5 goes in for x. My coefficient of a y is 1. I have no z's equals 1. So this right here is this system as a matrix. Feel free to pause here and give this a try if you'd like. I'm going to write it as a matrix, which means instead of the curly bracket, I'm going to put brackets on both sides. Instead of my equal signs, I'm going to put a vertical bar. My coefficients for my x's in my first equation goes in my first row. In my second equation goes in my second row. My y's are -2 and 1. And my constants are 7 and -5. So you can think about it in terms of your columns or in terms of your rows. Either way, we get to the same spot. Again, feel free to pause here and give this one a try. My first equation, if we look here, I have x's, y's, and z's. Y, z, x, y. So I have 3 different variables. They go alphabetically. So my first column is going to be for my x's, second column for my y's, third column for my z's. I replace my equal signs with vertical bars, and my constants go on the right. So in my first equation, it's already in standard form. I have 4 x's, -1y, 2 z's equals 1. My second equation, I have 1y, 5z equals 20. I don't have any x's, so I put a 0 there. My third equation is not in standard form. We have to have all of our variables on the left side, number part on the other. So I'm going to go ahead and add a y here and get 2x plus y equals 7. So my x column gets a 2, my y column gets a 1. I don't have anything in my z column, and my constant's a 7. And that is our matrix. In example 3, we're going to go backwards. We're going to start with a matrix and come up with a linear system. So instead of having our brackets here to show that they go together, we're going to use a curly bracket to show that these two equations go together. They're going to be alphabetical here. So this is going to be like my x's, my y's, my equals, and my constants. Remember, our vertical bars and equal, our numbers to the right are constants, and on the left side, they're variables in alphabetical order. So in my first row, each row is an equation. I get 5x plus, because it's +2, 2y, vertical bar means equals 7. In my second equation, I have 0 x's, so I don't even have to write those. I do have 1y equals 9. So there is my system. Feel free to pause here and give this a try. Top equation. Again, first thing I'm going to do is get rid of my brackets and put a curly bracket to show that these still go together in a system, but it's no longer a matrix. 2 with an x first, no y's, vertical bar means equals 6. 5 first is x, minus 2y, remember it's x's and then y's, equals 1. And there is my linear system in equation form. We can solve systems of equations using matrices very similarly to how we solve systems with elimination. We call each step a row operation because we're doing something to a row in order to get to the next one. Our goal is to use row operations to get a matrix of the form shown in the middle of page 176. Here our goal is to get our identity matrix 1, 0, number, 0, 1, number. So some constants there. Remember, this is like x, so it's x equals a value, and this is like a y column, so it's like y equals a number. So we're still trying to get it in that same format as we did before. The only difference here is that it's going to be in a matrix form. If we look at page 176 on the bottom, they have the take note for row operations. Some things that we can do here with matrices is we can switch any two rows. So our top row can go to the bottom, our bottom row can go to the top. We can also switch rows from different matrices as long as they're from the same system. So we maybe changed it and did some operations to it. We can pull back the original one if we want to. We can multiply a row by a constant. So here they took the bottom row and multiplied all of them by 2. We can add two rows together. So there they took and added the 3 and the 4, the 2 and the -2, and the 5 and the 6, and got a new row, 7, 0, 11. Okay, and then they just replaced it with another row. Doesn't matter which one. There they use the one that they got when they multiplied. Again, doesn't matter. We can switch any two rows at any point. And then we can combine any of those. So we can multiply and switch at the same time, the order or however we want to do that. So example 4 here is solving a system using a matrix. First step is to write it as a matrix. So here, remember, x goes first, then y, equals becomes our vertical line, -1. 2, 5, 4. Our goal is to get a matrix that looks like this. So the first thing that we're going to do is we're going to try and find one of the zeros. We're going to try and get rid of our column. So looking here, I don't have opposites, so I can't add these up to get a 0 yet, but I can multiply, just like we would with elimination, to get opposites. If I multiply that -2, I multiply the entire row by it, just like I would an equation. And I rewrite my bottom row. Now, I have opposites, so I can go ahead and add these two rows up. Row 1 plus row 2. It's going to give me 0, -3, 6. And I'm going to put another row in there. Doesn't matter which one, I'm going to pick the bottom one here. 2, 5, 4. I found a 0. Now we're going to go counterclockwise and try and find the 1 that goes with it. So if I have -3, in order to get it to 1, we're going to use multiplication here. I'm going to multiply by -1/3. It's like dividing by -3. Anything divided by itself is 1. But with matrices, we use multiplication. And I again do that all the way through. So 0, 1, -2. And now I've accomplished a goal here. I got a 0 and a 1. I know my b value is going to be -2. I'm going to put a star there. And I'm going to put my row here. Just bring it down, my bottom row. Now it's like we're going to start over. I'm going to keep going counterclockwise and try and find a 0. If I have a 5 and a 1, I can get opposites here, which is what I need in order to get a 0. Again, it's like we're just starting over by multiplying by -5, just like I had to multiply by the 2. So I'm going to have 0, -5, 10, and 2, 5, 4. Now that I have opposites, I can go ahead and add these up. Row 1 plus row 2. It's going to give me 2, 0, 14. And the row that I'm going to pick here to replace it with is this one, because I starred that one because that's part of our solution. We need that. So now I've got the 0 I need. I'm going to keep moving along and try and get the 1. Well, to make that 2 a 1, I got to multiply by 1/2 or divide by 2. We do that all the way through and I get 1, 0, 7. And I bring down my bottom row. And now we've accomplished our goal. We have our matrix in the form 1, 0 a number, 0, 1 a number, and we can write our ordered pair x, y. Keep in mind it has to be with the 1, 0 on top and then the 0, 1 on the bottom. So we get opposites, we add them up, we multiply by our fraction to get it to be 1. We repeat, get a 0, get a 1, write our answer. Very similar to how we did with elimination. Make sure we keep these as matrices, so keep them in your bracket so you know which two you're using, and we can go from there. I'm going to stop this here and I'll finish up the last example in another video.